Hello, my name is Arsh and I'm on Team 32. Now this is my rover design. So this is a rover designed to, traverse the Mars terrain and give us, information about what the surface of Mars is like. Now let's look at the specific mechanisms that I have on this rover. First, let's start with this wheel pod. The wheels the wheels here are inspired by the Perseverance rover wheels, which are made in order to last a longer time, right? This tread design here, right? And so now that's important, right? To have extra life on your parts, right? And so in that sense, this wheel tread, this wheel, and so that's important because this robot's out in space and has no chance to get any real maintenance on it. Once it's out there, and as a result, these parts just have to last as long as possible. So that's why we're using this wheel tread design, as it's been optimized by NASA engineers to be a long-lasting tire. And on that note, I decided to make a change to the design used by the Perseverance rover, and instead of, because their design had a cantilevered wheel, right? Their wheel system mechanism was cantilevered. I thought that that would cause a lot of stress on the members, right, in that mechanism. And as a result, I actually created a more enclosed mechanism here, and I structured the module to be non-cantilevered and more stable, and that should in turn increase the life of the mechanism. Now for my suspension, I have a rocker boogie suspension mechanism. Now this is a standard mechanism in rover design, right? And so I made my one using pipes, as pipes are hollow and they can, and so that reduces the weight of the rover as a whole and the mechanism, right? And so now weight reduction is important, as this rover has to support itself for a long period of time, and so that will just reduce the load on the rover as a whole. And now moving on to the arm mechanism, right? What I have here is a 4 degree of freedom arm. So now I chose to have this many degrees of freedom because the more degrees of freedom you have, the more control you have of the arm in 3D space, and the more options you have for the arm to move in, right? And so what we have actually is that as at the base, we have a turntable, right? That's the first degree of freedom, and then we have 3 other degrees of freedom as you go up the arm, right? And so now the one at the base, that turntable, is actually actuated using gears. And then in addition, on the end of the arm, we have a claw mechanism, which is also actuated using gears. So now gears allow us to create a gear ratio, which allows us to have more precise control over the turning of the arm. That's why I put a gear mechanism in the base versus direct driving like the other components, the other joints on the arm. Right, so I had a torque ratio, so that allows us more control. And then the claw, you would only need one actuator if we have the 2 claws linked together with the gear mechanism. And then over here we have the LiDAR camera. Now this is able to swivel in 360 degrees. And so that allows us to map the surrounding environments and give us information about what the terrain is like, right? Because it's a depth camera, it can give us give us an accurate mapping. And then finally here we have this solar panel, which I chose this because the sun is a very consistent source of energy on the planet Mars, and so it would be able to power the robot for a long period of time sustainably. And now some interesting aspects of the design here is that first let's look at these bearings. These bearings here are ball bearings, and so I use them because they reduce friction in mechanisms, right? And some interesting parts of this is that I designed the specific of all the balls in this bearing, and I designed the housing, and it's a fairly realistic bearing design CAD design. And in addition, something of note is this isogrid pocketing, which I used on the chassis, right? Now the chassis here is mainly sheet metal that's bent into the shape, as you can see, and then I have the ends, right, to the back and the front having isogrid pocketing, which is a standard for, you know, aerospace applications to reduce weight whilst maintain the strength due to the triangle shapes, you know, helping maintain the strength while still, you know, cutting into the material. You know, this is my Rover design. Hope you enjoyed. Thank you.